Hello everyone, in this lecture we will talk about mechanical properties of materials. In earlier lectures we have talked about basic concepts about biomaterials, some of their properties and we have discussed bulk properties, surface properties, and we have also discussed how to characterize surface properties of the material. So we will mostly focus on the mechanical properties, those properties which are of biological importance. For most of the biomedical applications, the materials which are used, two properties are mostly important in each biomedical for each biomedical application. These two properties are strength and reactivity. Strength in terms of the mechanical strength and reactivity in terms of the chemical reactivity. These are two important parameters which need to be studied. In mechanical studies, different mechanical properties are studied, different mechanical properties are measured, and their dependence on the structure and their dependence on the composition is also studied. And in this lecture, we will also know about how to control these mechanical properties, depending on depending on how we change the composition and how we change the structure of the material so that these mechanical properties are modified or they are tuned according to the requirement. The materials that are commonly used in biomedical application may have these following properties, or these properties may be studied in different materials. For example, mechanical properties, chemical reactivity, thermal reactivity or thermal property, optical properties, electrical properties, and magnetic properties. These all properties are studied for any biomaterial. The first mechanical property that we are going to study is the elastic behavior. In the elastic behavior, the load is applied and the extension is studied. So when the load is applied in the form of tensile force, when it is applied, the material will extend in a direction, and that extension is proportional to the amount of load that is applied. So there is a linear change in that. When we increase the load, the amount of extension that happens because of this tensile force or because of this load will also increase. This elastic behavior, it is studied by Hooke's law. Robert Hooke have given the law in 1678 to study elastic behavior, and Hooke's law states that most of the solids behave as an elastic material. They behave as an elastic manner, like in a spring, if the load is not too large, up to some extent. For example, when we increase, if it is a material and we apply the load on the material up to some extent of load, the extension is directly proportional to the load. But after some extent, after increasing the load to very high extent, in that case, this linear correlation was not is deviated. So in the elastic behavior, the load is directly proportional to extension. When the more load is applied, the extension also increases in the direct proportion. When these materials show the elastic behavior, so two terms emerge from that. First is the stress. The stress is the normalized load, the load that is applied to the material, and its units are force per unit area. And when the load is applied, there is a deformation in particular direction, and this deformation is called a strain, and this strain is defined as change in length divided by original length. So the deformation by the so there is a strain or deformation in the material when the stress or load is applied on the material. So this extension for a given load, it varies with geometry as well as composition of the specimen. So it is therefore difficult to compare the relative stiffness of different materials, or to predict the load carrying capacity, or it is difficult to predict the elastic behavior of the material with different compositions. To resolve this composition, the load and deformation can be normalized. For example, the load is reported as a load per unit of the cross-sectional area, and the deformation is reported as the elongation per unit of the original length over the elongation over which the elongation occurred. As you can see in this figure, the load is applied, the force is applied, and it is applied, it is and it is measured per unit area, load applied per unit area, and elongation is the change in the length over the original length of the material. And this normalized load is called stress, and this normalized deformation is called strain. So the tensile stress, it is the force per unit area, and the tensile strain is the length divided by overall length, change in length divided by original length of the material. Another important aspect of this tensile stress and tensile strain is that in case of tensile strength, in case of tensile stress, stress is force per unit area, and this area is perpendicular to the surface on which the force is applied. For example, F is the force applied and A is the cross-sectional area which is perpendicular to the force. For example, force is applied in this direction and this cross-sectional area is perpendicular to the surface on which the force is applied. And this tensile strain is the change in length. For example, delta L is the change in length, and divided by the original length. So this is the original length, and but this change in length is in the direction of the original length. For example, this is the original length, and change in length is also in this direction. It is not in here, it is not here. So this is the tensile stress and tensile strain. In tension and compression also, the load is applied, it is perpendicular to the loading direction, and it is called tensile stress, and change in length is parallel to the original length, which is called tensile strain. Here in this case you can see that if the load is applied here, it is perpendicular to this. And here in this area there is a compression, and in this area there is a tension. So this is the when the load is applied in some area there is a compression, in some area there is a tension. In earlier slide, we have talked about tensile stress and tensile strain. Here is another term that is the shear stress and shear strain. So in case of shear is applied or shear stress is applied, the shear stress is applied when the load is applied that is parallel to the supporting area. For example, in that case, the compression is applied, and is compression or the shear is applied, it is parallel to the surface. Or here in this case, when this force is applied, it is parallel to the surface. So so this shear is called shear stress, or this load is called shear stress. And the change in dimensions, or the change in length, or the change in or the deformation, if the deformation is perpendicular to the surface. For example, this is the this is the length, and this is the change in length. So this change in length is perpendicular to this original length. So in that case, it is called shear strain, and the basic formulas are actually same. For example, in stress is force per unit area, and strain is length divided by, or change in length divided by original length. But there is only the change in this parallel and perpendicular things. So if I can tell you once again, the shear stress is the force per unit area, F is the force, and is the cross-sectional and A is the cross-sectional area which is parallel to the force. And in case of strain, is delta L by L. L is the change in delta L is the change in length which is perpendicular to the reference length or original length. So from these tensile stress and strain and shear stress and strain, two formulas emerge. In case of tensile stress and strain, delta is equal to E epsilon and in case of shear stress instant, tau is equal to g gamma, and this is the delta is the this is the stress, and epsilon is some proportionality constant, and E is the proportionality constant, and epsilon is the strain. And here also tau is the stress, and G is some proportionality constant, and gamma is the strain. So these in these two equations, the E and G, which are emerged from the Hooke's law, and they are the proportionality constants. And this E is called Young's modulus of the material, and this G is called shear modulus of the material. And these moduli, for example, Young's modulus or shear modulus, they are represented by the they are represented by the shear and strain, the elastic portion of the stress versus strain curve. Sorry, I will repeat it. This moduli, elastic moduli or Young's moduli, they are measured by the slope of this stress versus strain curve. In tensile stress and tensile strain curve, uh, if we plot tensile stress versus tensile strain, the slope of the graph, which is linear, actually is up to some extent up to fracture stress. The strain actually proportionally increases as compared to tensile stress. So the more the slope, the more is the Young's modulus, and in case of shear stress and strain, the more the slope, and more is this shear modulus, that is G. And now maybe in your minds you can say that we know what is stress, what is the strain, but we don't know what exactly in material or these proportionality constant represents. Actually, these proportionality constant, they represent the inherent properties of the material. For example, the strength of the material, interatomic interactions. These are constants, and these are constants for each material. You can get the idea. For example, in case of some materials like diamond, tungsten, aluminum oxide, these are very strong materials, and in that case these moduli will be very high at a given stress and strain. For example, the materials which are very soft and which have weaker bonds, in that, like polymers, gold, these moduli will be lower in those materials. So here the same thing is explained in correlation with the stress and strain. For example, the material with strong bonds, that means diamond or some metal oxides, it has a high moduli. That means at the given stress there is very small deformation or very small strain. And in the materials which have the weak bonds, for example polymers, they have lower moduli. That means at a given stress, at a given some constant stress, there is a very large strain or very large deformation, because there are weak bonds in this material. And another term on which mechanical properties depend, or isotropy and anisotropy. If the mechanical properties are same in all directions of the material, then the material is isotropic. And if the properties are not same in all the directions, that that means the material is anisotropic. For example, bones, ligaments, these are anisotropic materials. Like I explained in the earlier slide, in stress versus strain, maybe the tensile stress or shear stress or shear strain. In that case, the moduli will change according to the slope. For example, if the slope is high, for example, in that case, on in for example, if the very less this stress is applied, there is a there if uh, in this case, when a large, when the Young's modulus is high, that means, if we say in that point, that means uh, on at a particular stress there is very less strain. But if we get if if for the other material, if this at the same stress the strain is very high, that means in that case the material is very soft, and it is Young's modulus is low. Same is the case with this. For example, at this shear stress, If the material is hot, that means the Young's modulus is high. That means it is very hot. There is very small deformation in the strain, or there is a very less strain or small deformation. But at the same stress, if we see that at the same stress here, the deformation is very less in case of materials which have low moduli or shear moduli. So I have already talked about this Young's modulus and shear modulus for the materials which are very hard. They have the high moduli, and the materials which are weak, they have the less moduli. So this moduli, it depends on the inherent properties of the material, the interatomic bonds or strength of the material. These moduli. So to test the mechanical properties of material, so mechanical testing is important to know the load deflation or stress strain test. This is the instrument in which this stress strain test or this mechanical testing can be measured. So here in this portion, the specimen is placed, and specimen is there are proper methods by which in which this specimen is prepared. Which I will talk in the next slide. And these are the jaws. In these jaws, the specimen is tightly placed so that when the tension is applied, it will not slip from these jaws. And the material which is used in these jaws and in this load cell, it is very strong from the material which is tested. So it is the strongest material. So that there is no change in this material, but only this material is studied. When this material is placed in these jaws, the crossbar and the crosshead, this crosshead and this crossbar, it is moved up and downwards so that the stress is applied on the specimen. And this load cell, it determines how much load is applied, or how much force or is applied on the specimen. And this load cell, it acts as a somewhat like a springs, which spring scale which measures how much load is applied. You may have seen that the spring type of weighing balance, in which there is a spring. When the load is applied, the spring extends to some extent and it gives the measure of the weight. Here the load cell acts in the same way, and it tells us how much force is applied on this material. For a valid determination of the fracture properties or fracture point of the material, the fracture should occur at this point between this, and it should not occur at the grip. If it occurs at the grip, it is considered that it has been occurred because of these jaws. If it occurs at the grip, these are the valid measurements. So the fracture point is measured. So the stress is applied up to the fracture point. First, there is a strain, and after the elastic strain, at the some a point reached where this material fractures. So proper standards, their specimens should be standardized in each testing or in each measurement. Actually, specimen, if you are repeating this tensile testing, so specimen in each case should be same, and we must ensure the reproducibility of the samples. So in that case, American Society of Testing, American Society for Testing in Materials, they have published some protocols for different varieties of tests for mechanical testing, which should be followed uh, before going for testing any materials. So here in this picture you can see that the material is first processed to be to be placed before placing here for the mechanical testing. So these all parameters should be taken on the note of, and in each case, if we are repeating experiment, these parameters should be same in each case. So this is actually the machine where there are these jaws, and the material is placed in these jaws, and these screws are tightened so that it fits here. So some of the important parameters that we need to consider, and these dimensions should be same in each test if the material if different types of materials are tested for the comparison. So this I0, it is the gauge length, from this to this. In this portion, actually, we are studying this change in the strain or elongation, whatever the things we are studying in this I0 portion. And the changes should we only consider change in this portion, for any tests. This I1 is the grip distance. So this I1 is the grip distance. So the group should be from this to this side. Group should not extend in this portion. Also from this side, group should not extend from this portion. It should be limited to this length. I2 is then overall length. This is the overall length of the sample. P is the width of the narrow parallel portion. This is the width of the narrow parallel portion. P1 is the width of the ends. This is the width of the ends, and T is the thickness of the material. So all these parameters should be constant in each case if we are repeating the experiment, or if we have 4 to 5 different samples and we are comparing those samples. In each case, the dimensions should be exactly the same, so that there should be no variability in results because of these parameters. In this slide, we will talk about bend test and torsional test. In both these cases, the material actually in this case there is no grip, or that is not required, so that we have to prepare the sample for the grip, but material should be same. Dimensions of material should be same in all the cases, and that is the much needed thing. As you can see in this test, the material or the bar, it is placed on the rollers, and this piston, the load is applied. When this load is applied, in this inside portion there is a compression, and in this outside portion there is a tension. So because of this, here there is a tension and here is a compression. So this bend test is used to know the strength of the material, bending strength of the material. Another test is the torsional test or rotational test. In this case, the rotational load is applied. For example, if the material bar is here, the machine this is the material bar, the machine rotates it like this. So in that case also the strength of the material is evaluated. In all these parameters, strength is evaluated in different ways. For example, in bending test, the bending property is evaluated. Torsional test is rotational property is evaluated. On the basis of the tests, the materials are fabricated according to according to the different requirements, and according to different requirements different tests are performed. This is all in this lecture, and there are some other mechanical tests which I will cover in the next lecture. Thank you for your attention.